Let's interpret the gradient. So from the directional derivative, you know that the directional derivative in the direction of u hat at the point AB of the function f is given by this formula. So you take the gradient and you dot it with the directional derivative. Now, what is the dot product? The dot product, we defined it as the magnitude of the first vector, this here is a vector, right? Times the magnitude of the second vector, the magnitude of a unit vector is just 1, times cosine theta. Now, what is that theta? Theta is the angle between u hat and the gradient, okay? So for the gradient not equal to 0, we have some observations that will help us interpret the gradient. When theta equals 0, and what does it mean for theta to equal 0? That means that u hat and the gradient are in the same direction, okay? So when that happens, when theta equals 0, the directional derivative is at a maximum, okay? Why? Because cosine of 0 is 1, and that's the maximum that cosine can be. U hat has just magnitude 1, okay? So for all intents and purposes, you could kind of ignore that since it's just 1. So we have that when u hat points in the direction of the gradient, you get the maximum rate of increase. And so what then does that tell you about the gradient? It tells you that the gradient points in the direction of greatest increase of the function, okay? So another way to say that is the gradient points along the steepest ascent. When theta equals pi, so that the gradient and u hat are in opposite directions, so u hat is in the direction opposite of the gradient, you get the maximum rate of decrease. Another way to say that is that minus the gradient points in the direction of the steepest descent. Okay? And notice, I mean, when theta equals 0, you have cosines 1, so you have the direction. So we have that the gradient points in the direction of maximum increase or steepest descent. Well, what is the magnitude now of that steepest rate of increase? What is the magnitude of it? Well, it's the magnitude of the gradient. Okay, you could see that from here. So the magnitude of the steepest ascent is given by the magnitude of the gradient, and the direction of the gradient gives you the direction of the steepest descent. Okay, when theta equals pi, now when theta equals pi, u hat is pointing in the direction opposite, and you get the steepest descent. Okay, and what is the magnitude of the steepest descent? The magnitude is also the gradient, the magnitude of the gradient, but this time you get a minus sign due to cosine of pi being negative 1. Okay. What about when theta equals pi over 2? So that u hat points in the direction orthogonal to the gradient. Well, then cosine of pi over 2 is 0, and so there is no change along directions orthogonal to the gradient, okay? And you can notice that when there is no change, okay, of the function along a particular route, okay? Let's take a path r of t, for example. Here r of t is just some path. It's the vector function whose trajectory gives you a path. So if the function does not change, right? Say it's equal to a constant, so you get a level curve, right? When the function is equal to a constant, you'll get a level curve. Well, the derivative of that constant will give you 0, right? But from the chain rule, we have this, okay, which could be written as a dot product in this way. I mean, you have partial f partial x. That's the first component of the gradient. Partial f partial y, partial f partial z. The r prime, where is that r prime? That's dx dt, dy dt, dz dt. That's r prime. And what then do we learn? we learned that the gradient of f is orthogonal to level curves and level surfaces. I mean, r of t is a path that would keep us on a level curve or level surface due to this relation here. So this is basically telling you you are on a level curve or level surface. The derivative of the function, the height of the function, is constant along that path. We then have that the gradient is orthogonal because this dot product is 0. The gradient is orthogonal to level curves and level surfaces. So to get a better idea, take a look at this visualization here. Here, notice on the xy plane that we have this green level curve. That green curve there is a level curve, and the blue vector that you see there is the gradient, and the red vector is minus the gradient. Okay, the black vectors are orthogonal to the gradient. Now, the black vectors are in the direction of the level curve, so they're tangent to the level curve. All right. And you see here that the gradient is orthogonal to the level curves. It makes a 90 degree. And what do I mean by orthogonal to the level curve? It means that it's orthogonal to the tangent to the level curve, okay? To be more precise. So this here is a visualization that summarizes the conclusions that we made. Notice that the gradient points in the direction of steepest descent, okay? And we could change the point A and B. Okay, so here we're changing A. Still, the gradient points in the direction of steepest ascent, in the sense that if you want to get, if you're on this paraboloid and you want to get to a higher point in the fastest, with one step, if you just have one stride and you want to get to the highest point with one stride, we'll move in the direction of the gradient. If you want to get to a lowest point in one stride, move in the direction of minus the gradient. And if you don't want to have any change whatsoever in one stride, move in the direction of the black vectors, which are tangential to the level curves. Just as the gradient points in the direction orthogonal to a level curve, I mean, consider this orange surface there and consider it a level surface, okay? So the gradient of this function of 3 variables points orthogonal to the level surface in much the same way that for functions of 2 variables, the gradient points orthogonal to the level curve. This fact about the gradient pointing orthogonal to the level surface will be used to derive an equation of a tangent plane. So it is important to at least conceptually understand what's going on there.